Hi everyone, today we'll talk about the matrices. The matrices is a very popular thing in mathematics. We use this in many applications in solving system of linear equations and or differential equations and others. So first of all, we start the definition and notation for matrices. The matrix is a rectangular array of a number. These numbers are called elements of matrices. For example, if we have this as symbol example for matrices, we call this A. Either we can show matrices with this in this form, or we can show in this form also. We can see in some books. So this is a very simple example for matrices, and this is called the rows of matrices, and this one is, let's say here, in the column of matrices. So the first row elements, second row elements, and first column elements, and second column elements. And so this is a very simple example for matrices. Also, you can see the example 3.1, which is 3-form matrix. To show the notation, dimension of matrix, so we first show the number of rows and then the number of columns. For example, in this matrix we have 2 rows, and that's why we say the number of rows. And the cross product is kind of show the dimension and number of columns in 2 and 2 matrix. Or if you have, for example, matrix 1, 2, 3. So to define the dimension of this matrix, we say the number of rows is 1 and number of columns 1, 2, and 3. It's called 1-3 dimensional matrix. And in the example 3.1, you see the matrix with 3 rows. First row elements, second row elements, and third row elements, and 4 columns. And also in this case, we say that it's 3 and 4 matrix. After this, we have some special matrices. We define this to make our works a bit easier. The one of them is a square matrix. Is a matrix with the same number of rows and columns. The example for square matrix is 2 and 2 matrix. For example, matrix A is square matrix, matrix B is square matrix. Or we can show this 1, 2, 3, 4, 5, 6, and 7, 8, 9. Let's say it's matrix C. The dimension of this matrix is 3 and 3. It's also called square matrix. And also we can say the matrix with 1 row and 1 column, for example, 1 or 2, or let's say 15 is 1-1 matrix. It's also square matrix, you can say. The next one is row matrix. Is a matrix with only 1 row we have. For example, this is row matrix. Or we have only 1 row. And meanwhile, we can define the column matrix, which we have only 1 column. For example, we say A star is 0, 1, 2. It's column matrix called. In example 3.3, you can see that, another 2 examples related to row matrix and column matrix. Well, matrix notation. So why we need matrix notation? It's again for some conditions of matrix. We will use this matrix notation. How we define the elements of matrix. Well, first of all, this is the notation for matrix, how we define each element of matrix. This is example 3.5, it's kind of formula or notation for matrix. I will explain this on the example 0, 3, and 5. Let's say it's matrix A, right? So the first is the element in the number A11 is equal to 1. So for example, this is, the first one is shows the first row and first column element. First row and first column element. If we have, for example, how to notate this element, first we need to show first row and third column element. A13 is equal to 4. So if you say that, tell me the element of A22. So we should find second row, second column element is equal to 3. So this is about the matrix notation. Either we can show this as A in index 2, 2, or we can show in this form 2, 2. This is also we can see in some books. Next one, it's another example. Example 3.7 is related to matrix notation. Well, equal matrices. If we have two matrices, we say that these two matrices equal if each element of this matrix are equal. Only in this case, we say that these two matrices are equal. So, example 3.8 shows that we have two different matrices with dimensions 2 and 3. Then it says that under which condition, for example, these matrices are equal, it means the first element A11 must equal to 1, or A12 must equal to 2, and others. Well, this we defined under which conditions the two matrices are equal. Next one is another notation, zero matrices. How we define zero matrix. So we said that any dimension, the matrix with any dimension, and only all elements are equal to 0, it's called zero matrix. For example, this is the zero matrix, right? All elements must be 0. This is, for example, 0, 0, 0. Another example for zero matrices. Well, for example, this one 0 and 0. Again, it's a zero matrix. So to be zero matrix, we don't need to be a square matrix. We don't need the number of rows must equal to the number of columns. What only we need, the all elements must be 0. We call this zero matrix. You can see example 3.9, another for non-square matrices, which is 0. So another notation for matrices is transpose matrix. We notate this matrix by A to the T is the transpose of the matrix A, right? So it shows in the power T, it shows transpose of matrix T. What's the meaning of this? Transpose of matrix means that we change the row element to column element, and only this way we get transpose of matrix. For example, we have the matrix A is equal to 1, 2, 3. So to find A transpose, what we need to do, very simple, we need to make column elements to row elements. So the definition of transpose matrix, we change the row to column elements or column to row elements. So here, column elements, we change this to row elements. It's transpose of matrix A. Also, we can find a transpose of any dimension matrix. We don't need it's a square or it's row or it's column. We can find any dimension. Well, for example, another one is 2, 3, 4, 5, 0, and 1. Let's say B is the matrix, and what's the dimension of this matrix is 3 and 2. The number of rows, 1, 2, 3, number of columns, 2, right? So B is a matrix with dimensions 3 and 2. So what's B transpose? You need to change row to column. It means that now our dimension B transpose will be 2 and 3, right? Because we need to change the place of row and columns. Also, this is for the elements of the matrix. It's 2, 4, 0 will be now row elements. It was column elements, now it's row elements. And 3, 5, 1. So, sorry, I need to write symmetrically for it. 4 and 5, yes. Well, B and B transpose of the matrix. Also, you can see example 3.11, the matrix A is given by notation of each element, A11, A12, and etc. How we find transpose of A? Again, we make the row to column elements. You see, in this here is A11 and A21 is column element. Now A11 and A21 is row elements. Well, it's another example for transpose of matrix. If we have a row matrix which is on the one row, transpose of this will be column matrix. If we have column matrix, transpose will be row matrix. Well, so now we need to define the symmetric matrix. Under which condition we say that the matrix is symmetric? If if the matrix A is equal to A transpose, it means that this matrix is symmetric matrix. For example, of course, to be symmetric matrix, it's crucial, it's very necessary we have this matrix is square, because we said that when you find transpose of matrix, you need to change the row to column elements and column to row elements. And another condition we have, if we have two different matrices which are equal, we need to get the same dimensions for this. That's why A must be square matrix to get this equality. Otherwise, if A is not square, we have, for example, 2 and 3 dimensional matrix, what's transpose of this will be 3 and 2. So this matrix cannot equal. That's why symmetric matrix must be square. So, and this condition must be satisfied for symmetric matrix. I will give an example. Also, you can see some example 3.14 in the lecture notes, and meanwhile, I will give different example. Well, we have 1, 2, 3, 0 and 1, and this is 2, this is 3, let's say it's 4 and it's 4. Let me write this a bit more clearly. So 1, 2, 3, 2, 0, 4, so 3, 4, 5. So this is the matrix A. So what's transpose of this matrix is equal to, we make the row, column element to row element. Will be 1, 2, 3. First column, first row. Second column, second row will be 2, 0, 4. And 3, 4, 5 will be 3, 4, 5. So you see that all elements 1 and 1, 2 and 2, 3 and 3, 4 and 4, 4 and 4, 3, 5 and 3, 5. All elements are equal. It means that these metrics are equal and also symmetric. Another, how we know that this metric is symmetric, actually we don't need to find transpose of these metrics. We can see, we can take the diagonal elements, right, as a line. So this is a line. You see 2 and 2, 3 and 3 and 4 and 4. Another way, the easiest way to define symmetric matrix, right? Well, also you can construct symmetric matrix yourself. For example, you want to construct symmetric matrix. You take diagonal elements, any, right? Any diagonal element, and you take, for example, if you write here 3, to get the symmetric matrix, you have to take this line and symmetric. Here must be also 3. If you take here, for example, 1, here also must be 1. If you take here as 2, here also must be 2, because we consider these must equal. Well, this is symmetric matrix. 2 different examples, and you can see some example in example 3.14. And next one we say antisymmetric matrix. We say that A is said to be antisymmetric matrix if transpose of A is equal to negative of A. Not A itself, it's negative of A. A negative 1 is equal to A transpose. So to define this, first of all, we need to define the scalar multiplication to matrix, because we need to define negative A. What's the meaning of negative A? So we have scalar multiplication to matrix. It's about, for example, if we have scalar and if we have very simple matrix, 2, 2 matrix, right? So this is equal to define this, to define right this under the one matrix, we need to multiply each of these elements by this scalar. Will be 2. 2 multiplied by 0 is 0. 2 multiplied by 2 is 4, and 2 multiplied by 1 is 2. Right? So it's scalar multiplication. So negative A is another negative A, meaning that minus 1 multiplied by A, sorry. Yes. Is equal to, it means that we will multiply each element of A by -1. And to get antisymmetric, right? Well, antisymmetric definition of antisymmetric. Negative A must equal to transpose of A. We'll see some example related to this. For example, we have example 0 and 0 and 0. This is, let's say, -4 and this is 4. This is will be 5, this is -5. This is, let's 6, it's -6. So we can construct symmetric matrix again ourselves. So we have this equality, and we see that when you find the transpose of square matrix, we say that diagonal matrices don't change, right? Diagonal elements of matrix don't change. That's why to get this equality, negative is equal to positive 1, you need to get diagonal elements always 0. So it means that if you have antisymmetric matrix, you can say that diagonal elements 0, right? So after this, if it's -4, it must be 4, and 5, -5, 6, -6, the opposite sign of this, how we construct. If you find, for example, transpose of this matrix, again you keep diagonal elements, and you make this as, let's say A transpose is equal to, and this is A, yes, A transpose is equal to, this will be row elements, -4, 5. So this one, or again, will be second row elements, 4, 0, 6. This one will be again row elements, -5, 6, 0. So we need to get this equality. It's satisfied or not? We see that it's 4, -4. -5, 5. -4, 4, -6, and 6. All is opposite signs. And the same for zeros. That's why we have -A is equal to A transpose. Right? It means that this matrix is antisymmetric matrix, right? Well, again, we said that I want to mention to find symmetric and antisymmetric matrix must be square. And for antisymmetric, diagonal elements must be 0. You can be asked that. Give an example for antisymmetric matrix. What you should do, just take main diagonal elements as 0 and take the line, this, and take these elements with opposite signs. -4 and 4, 5 and -5, 6 and -6. That's all. You construct the antisymmetric matrix. Well, we'll define diagonal elements. We already talked about what's diagonal elements. Diagonal elements is we notate each element of each element of matrix. For example, what's the notation for this matrix? A11, A22, and A33. Right? If we have these equalities, 3, 3, 2, 2, and 1, 1. So we define this as diagonal elements, right? So also we see that Aij, the long surfaces are the same. The element is Aii. So we need to get the same places for row and column. First row, first column. Second row, second column, and third row, third column. Well, diagonal matrix. So another notation for matrix, a special matrix, we notate this diagonal matrix. Is a matrix with only diagonal elements non-zero. Other elements must equal to 0. So actually non-diagonal elements we say 0, not diagonal elements, because 0 matrix, square 0 matrix, is meanwhile diagonal matrix, right? So what we say, non-diagonal element is equal to zeros. So diagonal elements itself, diagonal elements can be 0, right? For example, we have this example. 0, 2, sorry. 0, 0, 0, 1, 0, 0, 0, 0. It's possible we have this matrix. It's also called diagonal matrix because all non-diagonal elements are 0. Meanwhile, we said 0, 0, 0, 0, 0, 0, and 0, 0, 0. In special case, this 0 matrix also, and also diagonal matrix, because this is main diagonal elements or diagonal elements, and non-diagonal elements are zeros. It's possible diagonal element equal to 0 or not for diagonal matrix. That's why in special case all square zero matrices are also diagonal matrices. Well, one example for identity matrix is 0, 0, 1, 0, 1, 0 and 0, 0, 1, it's 3, 3. Identity matrix, we define this as I. We generally write this I3 and 3. Or if you have given, for example, I, 2, 2, it means that 2-dimensional identity matrix, right? And also you can see in 3.18, example 3.18, you'll see 4 identity matrix, 2 identity matrix, and 1 identity matrix, 1 identity matrix. Well, next one is for identity matrix, we have this condition: n matrix plus identity matrix is equal to this matrix. Square matrix must be 3, 3, right? For example, this means that, let's say A is 3, 3 matrix, this I must be 3, 3 matrix again. Or A is, for example, 4, 4 matrix, this must be 4, 4 matrix again. So that's why if you have this notation, it means that I must be in the dimension of A. Well, triangular matrices, we have two forms of upper triangular matrix and lower triangular matrix. It's a square matrix, only we're talking about square matrix for upper and lower. Square matrix with only 0 elements below its diagonal elements. So it means that upper elements is non-zero or maybe 0, but in downside of diagonal elements must be all 0. So for example here, example 3.20 and 3.21 is for 4 matrix, and I will give example for 3, 3 matrix. For example, we have 1, 2, 5, 1, sorry, it must be 0, 2, 5, 0, 0, 6. It's upper triangle matrix, you see? It means that lower elements must equal to 0. It's example for upper triangle. We will see, we'll use this while solving the the system of linear equations. Well, another example for lower triangle matrix, it's let's say 1, 0, 0, 2, 5, 6, and 5, 4, not 6, sorry. 0 must be, and this is 7. Again, we say that in upside of the diagonal element is all 0, so we have in downside maybe 0 or non-zero. For example, if we have this is 0, let's say 0 and 1, it's also the lower triangle matrix, right? Well, one application of matrix, how we use this, why we use this, it's rotation matrices and computer graphics. So why we need this? It's kind of the main and the first and main application of matrices, how we use these matrices. So we have this formula, you see, x5 theta is equal to cosine theta, sine theta, and 0 for first row element, second row is minus sine theta, cosine theta, and 0, and third row element is 0, 0, and 1. This is kind of formula. So why we need this formula? Imagine we have 3D, right? It's x, it's y, and this is, let's say, z, right? And we have this point, x1, y1, z1. So, we have the angle theta, right? So in this formula, what's the meaning of theta? So this is a point, right? This is our point. Next case, we have rotation matrix. Why we need rotation matrix? If we convert x and y by the angle theta, for example, we convert x and y by the angle theta. It means that we have new, let's say, new coordinate system. Let's say it's y dash and x dash. And this is the angle theta. This is the angle theta. It means that we have the previous coordinate system x and y and z. And now we convert the plane where x and y is situated. The plane, we convert this, right? It's kind of plane x and y. And this is z. And when we don't touch z and when we convert x and y only, we have some angle which we convert x and y. It's kind of, we get the new coordinate system, y dash, x dash. And how we convert this? We convert this by the angle theta, right? And we have this point in the previous coordinate system, in the coordinate system x and y. And we need to convert this to new coordinate system, y dash and x dash. To do this conversion, we need to first construct the rotation matrix, which is given r, x, y, and theta, rotation matrix. Then after this, we need to find the elements of this point in the new coordinate system, after converting this to, by rotating by theta, angle theta. For example, we have example 3.22 for this. We have theta is pi over 2, right? It means that this conversion is doing by pi over 2. And we need to find r, x, y, pi over 2 multiplied by v. So what's v? V is the coordinate system, the point. Let's say, for example, this is 3, 4, and 5. This is the coordinate of this point in the previous one, in the x, y, and coordinate. So after rotating this coordinate by pi over 2, we get the new point. So we get new point. Of course, this point will be changed. The elements of this point will be changed. So the new one, how we find? We find this by r, x, x, y, theta multiplied by v, right? It means that we multiply the matrix to matrix, right? This is a vector, we consider it as vector, or I give matrix with a point with these coordinates, and we'll get this formula. How we apply this? We only write this formula. Instead of theta, we write pi over 2 and we will get this. So I prefer to solve this after matrix multiplication, because we need to know matrix multiplication for this. So to see now, another one is matrix operations on matrix. Matrix addition and subtraction. Of course, to sum two matrices, we need to have the same dimension for A and B, and also to subtract one matrix from another, we need to have again the same dimension. We have A and B. So A plus B to define this, or A minus B to define these two, we need to have A and B with the same dimensions, M and N dimension, right? So this is about the sum and subtraction of matrices. You can see example 3.24. You have two same dimensional matrices. The result, we add each element. The first element plus the first row element plus first row element of second matrix. For example, second row element plus second row elements, right? So this is very simple, but what we need to know, only we need to have same dimension matrices for this. Multiplication by a scalar, we define this while defining the antisymmetric matrix. So if you have scalar multiplied by the matrix, we multiply each element of matrix by this scalar, we get the result. For example, 3.26 and 3.27 for this. So, manipulated laws of sums and multiplication by scalars. We have commutative laws for matrix A plus B is equal to B plus A. And if we have, let me clean here. Well, we have A plus B is equal to B plus A. We have lambda A is equal to A lambda, commutative law. And next one, associative law, if we have A plus B plus C is equal to A plus B and plus C. Or if we have lambda mu A, we can also write this multiplication of scalars, then matrix. Also we can do this, right? Distributive laws also is given lambda A plus B. We can open the bracket lambda A plus lambda B. The same for scalars, lambda plus mu multiplied by matrix A. We write lambda A plus mu A. Well, we have some conditions after these laws, some necessary and sufficient conditions. One of them is A plus B is equal to A if and only if B must be zero matrix, the first one. And the second one, A plus B is equal to 0 if and only if B is equal to negative A. Or if lambda A is equal to 0 if and only if lambda is equal to 0 or A is equal to 0. So if and only if means that if you have right side, also we have left side. Right? Necessary and sufficient conditions. Another important property for the matrix, if we have scalar and then matrix multiplication, matrix addition, and then transpose of these, we can separate, find transpose of all the matrices and this one. Well, example 3.28 is about this property. So it's kind of verified that A plus B transpose is equal to A transpose plus B transpose. It's a special case of this property when lambda and mu is equal to 1. Right? So how we show this, it will take probably about time to solve this, but end of the day we will get the equality true. First we find A plus B, then transpose. And in the right side of equality, we find A transpose separately, plus we find B transpose separately, then we add these two matrices, right? Again, we have an example related to transpose of matrix and scalar matrices. And now we come to matrix multiplication, which we'll use this in our future application of matrices, and also we'll show how we find the rotation of plane, the result coordinates of the point. Well, matrix multiplication of a row matrix times a column matrix. So I want to generalize these things. I want to generalize it to multiply two matrices. We have matrix A and matrix B. So it's about the matrix multiplication. So we need to, the number of row elements in first must equal to number of column elements in second one. For example, we have 2, 3, 1, 0, 1, 1 multiplied by 2, let's write different one, too many 2's here, that's 0, 4, 5, and 1. So now I will show the number of columns, right, is 2 here, and the number of rows is 2 here. It means that we can multiply this. Generally, how we generalize this? If we have A and B as matrix multiplication, we should have M, N multiplied by, it's about dimensions of this, and N multiplied by K. K. So this is the dimension of first matrix, dimensions of second matrix. So the number of columns of first must equal to number of rows in second one. Or in another words, we can say the number of row elements in the first one, which also shows the number of columns, must equal to number of column elements or number of rows in the second matrix. Only in this case, we can multiply the matrix A and matrix B, right? With these dimensions, n and n, these must equal. And the result matrix will be C, M, K, right? The result matrix will be this one and this one. Well, an example for this, 2, 3, 0, 5, how multiply this? We take row elements, multiply the column elements. 2 multiplied by 0. So, sorry. Result, we will get the matrix, right? Let me write from here. So, 2 multiplied by 0 plus 3 multiplied by 5. This is first element, right? Second one, 2, 3 multiplied by second column elements. We will write this in the second place of the row. So will be 2 multiplied by 4 plus 3 multiplied by 1. So we finished the first row elements. Now we go to second row elements and multiply the first column and second column elements separately. 1 multiplied by 0 plus 0 multiplied by 5, right? 1 multiplied by 0, 0 multiplied by 5. And second element of second row for the result matrix, 1 multiplied by 4 plus 0 multiplied by 1. This multiplied by this. So we finish second row. Now third row elements will be 1 multiplied by 0 and 1 multiplied by 5. Third row elements multiplied by first column element of second matrix. Well, 1 multiplied by 4 and 1 multiplied by 1. So the result is, let me write the result here. So this is 0 plus 15. This is 8 plus 3, 11, right? This will be 0. This will be 4. And this will be 5. And this will be 5. Right? So, what's the dimension of this matrix? Is 3 and 2, right? Number of rows, 1, 2, 3. And number of columns, 2. So, I want to show this one. Our matrix, first matrix is 3, 2 matrix, right? And second matrix is 2, 2 matrix. So I want to show this formula, n and n. It means that we can do this multiplication. And the result is 3 and 2. 3 and 2. See? Well, this is the general formula of matrix multiplication. Only in this case, n and n must equal to multiply this. Otherwise, it does not exist, we say it. We cannot do this operation. For example, if we have 1, 2, 3 multiplied by 2, 2, 2 and 2. So this is 3 and 1 matrix, right? 3 row, 1 column. And this is 2 and 2 matrix. So for this multiplication, we see that does not exist. It means that we cannot do this operation. It's impossible because this is the 2 and this is a 1 and this is a 2. They are not equal, and because of our conditions, the number of column must equal to number of rows, right? Well, that's why in this case we say it does not exist. Of course, yes. Now let me see what next we have here. It's about row and column matrix multiplication. Now we generalize this. Well, if we have the matrix M with 3 and 1 multiplied by matrix N with 1 and 3, right? 3 and 1 and 1 and 3. So what the result will be? The matrix L with the dimensions 3 and 3 matrix, right? The result of these two matrix multiplication because of this formula, right? Well, or we have K matrix 1 and 3 and matrix O 3 and 1. So this is, by the way, guys, this is the column matrix multiplied by row matrix, right? And this is here row matrix multiplied by column matrix. The result will be the matrix P with the dimension 1 and 1, right? So this is 1 and 1 matrix, not the element. So this will be something with A in matrix form, not as a scalar, right, guys? Not a scalar. Well, multiplication of matrix by a column vector. We already generalized this. So this formula for all cases. Well, guys, matrix multiplication, we have seen this. We give an example for this. This is general formula for this. Well, next one, we can see some examples related to matrix multiplication. Well, let me solve one question related to this. In this form, for example, we write 1 and 3 matrix, let's say 0, 1 and 2 multiplied by 2, 1 and 3, right? So the result will be 0, 1 and 2 first row element multiplied by first column elements. It will be 0 multiplied by 2 plus 1 multiplied by 1 plus 2 multiplied by 3. So the result is, this is 0 plus 1 plus 6 is 7. 1, 1 matrix. Well, next one, guys, about the manipulative law and for matrix products. The main thing, guys, here about the matrix multiplication, we have the main rule about this, which is really different from the set of real numbers or multiplication of real numbers and others, other form of multiplications. So we have A multiplied by B does not always equal B multiplied by A, right? Right? Well, we have this condition. A multiplied by B does not equal to B multiplied by A. And also in lecture notes, we have AB multiplied by C, associative law. We can change the place, A multiplied by B multiplied by C, right? So it means that we can multiply the result of A by the result of B and C. There are also distributive law, A plus B and plus C, we can write this separately. And also A plus B multiplied by C, we can open the bracket when the matrix in the right side of the bracket. Well, another thing, it's scalar and matrix multiplication together. If we have lambda multiplied by A and B in the bracket, we can first multiply lambda by A, then B, and also we can first multiply lambda by B, then A. So this is the main properties of matrix multiplication and also scalar multiplication. Another thing is transpose theorem, very essential one after this. So we have this rule. You don't have this equality, right? Well, next one, and even always, it's not possible to multiply this. I mean, if you can multiply A and B, it doesn't mean you can multiply B and A. Why? Because if A is 3, 2-dimensional, and B is, let's say, 1, 2 and 1-dimensional, right? This is about A, this is about B, right? So you can multiply this. Why? Because 2 and 2, they are equal. But if you change this, B and A, let's write here. What's the dimension of B? Is 2 and 1. What's the dimension of A? Is 3 and 2, right? So they are not equal. It means that you cannot multiply it. It's not possible. So that's why this is the main property for matrix multiplication. And also we have transpose theorem. If we have A and B, the transpose of this, or you can write this B transpose multiplied by A transpose. It's another condition for matrix multiplication. And how you show this? You can show this by finding the left side separately, find A and B, then transpose of this. Then in right side you find B transpose multiplied by A transpose after finding transposing. So you can see the example 3.35 and 3.36 for this. And also we have some examples here, but actually I don't think we have time, or I don't want to waste time by solving this because it's very clear. Well, commuting matrices, guys, I want to mention here. If we have A and B are matrices such that AB is equal to BA, we say that this is not true for all cases. For all cases, right? No, sorry. This is not true. Generally, this is not true. But we have some cases which A and B is equal to B and A, right? This is general formula, right? Because if you write these conditions, it means that we have some special cases which we have this equality. We have some special cases, but this is just very general formula. If A and B any matrices, so we have this condition. But we have some special cases which we have this condition. We say that these two matrices are commuting matrices. So A and B are matrices such that AB is equal to BA. We say that A and B commute, right? Not that in general we have this, we wrote this, and matrices don't generally commute. So you can see in examples 3.39, these two matrices commute. We have these matrices and this matrix. The result is this one, but meanwhile, if you change this, the result also will get this one. So main thing here is that, well, guys, to get this, we should have A and B square matrices, right? Because if we have A and B, M and N, this is N and K, right? So this is B is N and K, and what's A is M and N, right? So if you have this equality, it means that you have this multiplication, we have this multiplication. To get this multiplication possible, we have N and N here. And also to get this matrix multiplication possible, we should have K and M must equal each other. It means that K and M must equal. It means that both of them will be square matrix, right? Because it's N and K and K equal, so we have M and K is equal, and also we have N and N here is equal, right? So the result will be N and N matrix C, right? N and N matrix for this, and M and K matrix for this one. It means that this is also equal to N, right? Because of this condition, the result of this matrix for this is M and K. And for this is N and N. So it means that K is equal to M and is equal to N, right? That's why the both of them must be square. 3, 3 max multiplied by 3, 3, 4, 4 multiplied by 4, 4. Well, guys, this is about the matrix notation. So after this, we'll see some application of matrices. It's about system of linear equations, how we solve this. Is the main purpose to define, to construct a matrix is to solving system of linear equations by easiest way. So of course it's coming from the application of some word problems, and to talk about it we need some time, but I hope I will give some application of metrics, why we need these metrics. For example, example 3.40, it's word problems, which end of these word problems, we find the modeling of these word problems, we get system of linear equations, and it's, for example, this system of linear equations, you see. So, to solve this system of linear equation, we construct the matrix form of the system of these linear equations. And we have some special ways. It's called row elimination methods or Gauss elimination method, and also we have some ways for solving this. Well guys, that's all about the definition and notation of matrices. So after this I will try, I tried to give some application of matrices about the solving system of linear equations, and also solving the system of, solving the differential equations and others by applied some form of some properties of matrices. And that's all. Thank you very much. Bye bye.